So the last speaker of the session and the last speaker of the workshop is Xiyuan Lu, presenting on the topic of chip integrated visible telecom entangled photon pair sources for quantum communications.
Thank you for the introduction. Thanks for everyone to stay into the last minute. That's not easy. And thanks for the organizer to organize such an amazing conference. It really helps me a lot during the government shutdown for your financial support. I'm kidding here. But the reason I was able to come is because I'm officially affiliated with the University of Maryland. Although most of the time I spend at NIST, CNST. And originally, Kartik, my boss, is supposed to be here, give you a more broader view of quantum optics, covering the experiment we're doing. But since I'm here, I'm going to focus on the work, a specific work we recently do is on chip integrated visible telecom entangled photon pair source for quantum communication purposes. So I would like to first motivate this thing because so nobody is doing this in nanophotonic chip before. So the reason is really because we have a lot of useful quantum systems at the visible or shorter wavelengths. We have NV centers, silicon vacancies, very good, and some quantum dots, atomic wafers. A lot of them, by the nature of design, it's in shorter wavelengths. However, if we are really talking about quantum communication or a quantum network, we want to communicate between these quantum systems and send them to provide a task. But it's not going to work very well because if you look at the table here, the 3 dB attenuation, this is basically the 3 dB attenuation distance in the single mode fiber. And you can see at around 600, it's 300 meters, you get 50% loss. So it's kind of difficult to propagate it over long distance. Telecom photons are apparently the best option in this case, if not the only option. And we spend a lot of efforts engineering that because of optical communication. So that's the reason we want to do it for visible telecom pair source. And I also want to mention why we want to do it in nanophotonic platform. First reason, like as many speakers have already said, it's a good platform for future scaling and integration. So you can have very fancy, many functionalities out of one chip, which we are not doing it here. But the second reason is that I believe this is a real process for nonlinear optics because it really confines the light, confines the energy in a small device, and the efficiency get very enhanced, which I will show later. So before going this, I want to say visible telecom photon pair source is not the mainstream for people to do this type of task. I think the mainstream now is doing frequency conversion, which our group was doing this, have some work on this before. So the work here is led by Ching, who is a professor now at CMU. So he was doing forward mixing backscattering. It's a little bit special forward mixing process in that it doesn't have a spontaneous process, but like the two pump beams at two frequency, they can diffract the other beam to plus or minus the difference of frequency. So this is a SEM image of our device. The blue one is a silicon micro ring. The red one is a waveguide. We use a pulley waveguide to wrap around the ring to provide a better coupling in two bands, just 900 band and 1550 band. And this is a side wall. This is a cross-section image, and we can engineer the width and the thickness usually to change the dispersion to make the process works. And so to help seeing what is here, so here the bottom one is silicon oxide, about 3 microns what we typically use, and the blue one is silicon nitride core here. The cladding, it can be air cladding or oxide cladding. So in this work, basically there are two things we are doing here. The first thing is convert the photon within the 980 band. So here by putting two telecom pump we create a grating, a nonlinear grating with this frequency difference, so that we can convert this 980 either to shorter wavelengths or longer wavelengths. The other way we do it is we can put the pump to 1 to 1550, the other one to 980, so that in this case we can do a down conversion. So these are all at single photon level, but we are still using a classical laser, attenuated laser. So in recent 2 years, I would say, we are pushing it in, really using real quantum single photons. So the first scheme is using heritage photon pair, single photons from photon pairs. So here the platform are actually very similar. The quantum frequency conversion chip and the photon pair chip are very similar in dimension. So in principle, it could be easily integrated later on. The other thing we also try is to do conversion for the quantum dot. So I'd like to mention that for both work we have done, they are all within the 980 band. So for quantum dot, it makes sense because one of the application is here is really to bridging the difference from the quantum dot, because every quantum dot are like they're emitting at slightly different wavelengths. So in this case, we can bring them to the same wavelengths, and we show that we can keep the property pretty good. But then another useful process is actually down conversion, as I showed earlier. We haven't been able to done this one nicely. The reason is our manifolds. But the major reason is that whenever you have a pump laser, you create noise around it. So in this case, it amplifies spontaneous emission and the Raman noise in the fiber and some in the device. And interestingly, for our device, photon pairs also count as noise, because it's a telecom. The pump photon can create a lot of pairs, as you see in previous talks. So usually those are useful signals, but for us, it's really large noise. So if we are doing it in visible telecom, pairs, we actually have more difficulties. Why is that? Because now we are not doing 980 anymore. We're doing visible 600 or 700. You know, the material dispersion get very large when it goes to shorter wavelengths. So design is much more difficult. But the other thing practically is visible laser turns out is not very cheap. If you want at shorter wavelengths, narrow line width, high power, and stable, we have Tesafile and doing OPAs and stuff, but in an ideal world, you don't want Tesafile for every quantum frequency conversion unit. So that's the motivation. I want to do it with visible telecom photon pair source, and one past reason is what physics always like is doing entanglement swapping. It adds a little bit of motivation. So so most quantum memory, as I said, is in the visible or shorter wavelength scale. So if you want to do entanglement swapping, it's not going to work very well because of the loss. The whole idea of entanglement swapping is to propagate the entanglement over long distance. But then, so in this case, if we have a good visible telecom photon pair source, we could use a telecom photon for the bare state measurement for the entanglement swapping, and then we swap the entanglement from originally within each photon pair source to two visible photons. And if we can design these two visible photons to be the same to your quantum system, then you can entangle two quantum system at a distance. So this is eventually what we want to do. But this work is mainly focused on visible telecom photon pair source. So because of this, we have many requirements for this source. You cannot just be some random results. So first, the dispersion engineering is definitely important. You have to design it for visible telecom, and the design better to be flexible, so you can suit any or most of the quantum system you are working on. So you have some sort of tunability and flexibility. The second thing that's important is you want the photons to be narrow line widths within each visible or telecom mode. Usually, like for quantum system, you want megahertz to gigahertz. In some case, maybe even shorter, smaller, but that's kind of difficult for photonic device. And we want a high purity for this photon pairs. CR, you can think of it as a signal to noise ratio. So basically, you want CR at least larger than 100, because if it's smaller, like let's say have a CR of 10, entanglement swapping is probably not going to work. Then we of course want the photon pair to be bright, so the experiment doesn't take too long. And we want the power to be efficient. Sub-milliwatt is the best in terms of our efficiency and controlling the noise. But if you have a couple of milliwatts, it's fine. Above 10 milliwatts, things become not working very well. We also want it to be integrable. So one thing I need to mention is that this entanglement swapping scheme for photon pair source is not on demand. So it's because of the probabilistic nature of the photon pair source. We need to do it by time measurement. A good reference is this nature of this paper. And for photon pair source, there's a review about the requirements if you're interested. So currently, what's the status of the visible-telecom photon pair source? The major platform, as you see a lot over and over this few days, is Pipling or PPKDP. So these periodic pole nonlinear crystals are really efficient in quasi-phase matching, and usually people use it in waveguide, and we start to see some integration thing now, but people haven't done it for nanophotonics or integrated thing for visible-telecom photon pair source yet. So this is a typical experimental scheme. Because of this Pipling waveguide, they have broad photon pair generated out. So for this purpose, you need to filter them down like 100 times or 1,000 times. So you need an external cavity, which usually meter scale. But other than that, this system is pretty successful, and I think 90%, if not more, people are still using it. The other system is photonic crystal fiber. Photonic crystal fiber is good. You basically can do any dispersion engineering you can imagine. It's also in the fiber, which solves the coupling problem naturally. It does have some characteristics we don't want. It's broadband. With 1 nanometer sort of bandwidth, it's too different for us to use for atomic system. The CR is also usually low. Typically, the results are around 10, several tens. Also, femtosecond laser is required because there's no cavity enhancement, and the lengths are typically also quite long. So the other system was still lithium niobate, but in a let's say, more integrated system. It's not really on chip, but it's a few millimeter. So these devices are usually manually or semi-machinely polished. It's really a device of art, not a device of science. But it works pretty well in many applications. So in this case, it works very good in terms of narrow bandwidth and the efficiency. So typically, they only use a few microwatts or tens of microwatts. It's not apparently how to integrate this device yet, and CR by far is still low. I don't think the limitation is fundamental, but it's technical that because of the resonator is large, there are many modes there, and all of the high order modes you cannot filter it easily or even identify them. Having said that, there are many works that you can see in these few days. People are doing integrated Pipling in like Makalonka's group and Chang's group at Rochester, and I think Hongtan's group is also working on it, and it's getting very good process. It probably will catch on later. So, but as of now, I think no nanophotonic source for our application yet. So we propose to do it in silicon nitride for a couple of reasons. So for review for silicon nitride nanophotonics, please really look at this paper. But then there are many groups that are working on this. It's been pretty mature and not as mature as silicon, but I think better than lithium niobate at this point. And it has a large transparent window, so 300 nanometer to 6 micron, and it has N2 10 times larger than silicon oxide. So it's really suitable for this process. There are many outcomes, very exciting results from silicon nitride nanophotonics. FrequencyCom probably be a major one. Many groups have great results in FrequencyCom, not only FrequencyCom, but also soliton and octave spanning FrequencyCom. And recently, people use it for optical synthesis purpose. So there are a lot of activity going there. Also, we heard this afternoon intensively about the multi-frequency beam entanglement, which are very useful for whispering gallery type of modes to explore the the information inside these many modes. There are also harmonic generation and quantum frequency conversion, as I mentioned before. So it has been very fruitful platform. But however, for the photon pair source, it's actually not that good. We have some publications, but it's nowhere compared to silicon. And currently, it's limited to telecom band. Most people are working on telecom band apparently because of its usefulness, but also easy to filter based on the WDM on this optical communication technology. But in the telecom band, it's not comparable to silicon at this point. CR is really low. In our recent work, I mentioned before, like Qing actually do photon pair source in 900 band. We get a CR about 80, slightly better than before, but not too much different. So one thing is that we should really using silicon nitride for something like silicon cannot do. For example, for visible telecom source or wavelengths below 1 micron, so that we don't need to compare with silicon. But the other thing I want to say is that nitride doesn't have to be inferior to silicon. The reason is because of the closed band noise, usually limitation there. This problem can be circumvented if we have a large pump that's like separated very far away from the signal and you still have a lot of noise, but it doesn't matter. It's very easy to filter away. Actually, you don't even need a narrow band filter in that case. So the CAR definitely have room to improve if you do things right. The scheme we are doing is degenerate four-way mixing, and we heard it a couple of times before. And so here basically degeneracy means that you have two pump photons at the same wavelength, and then you generate two photons, in this case very far away, signal at the red light and either at the telecom 1550. So the spectral separation is 250 terahertz. So one thing I kind of force myself to do is to do single mode engineering. I can't emphasize how I think this is important, although it's not a common thing in nanophotonics, especially within this large dispersion design. So you need to spend some effort in it, but I'm going to show it later on. There are tricks to do it, and I think it's totally worth it. So this is a coupling scheme of our device. We have a microring in the center and a pulley waveguide like before. This pulley waveguide this time is used to couple the silic pump beam and the silic signal beam, which is in the red light. The straight waveguide is used to couple the telecom beam. So we are using L cladding so that we can separate the coupling tussle very well. So they really don't couple each other. So here is the SEM image, and in this zoomed area, we show a pulley waveguide coupling and straight waveguide coupling. So for more details for the coupling, please check our paper. A little bit introduction about whispering gallery mode. Some of them may be very familiar with it, but it's basically, you can think of it as a total reflection inside of the microring. And there are standing wave with it. There's a standing wave mode number, or we call it azimuthal mode number, M. So the electric field just oscillates up and down in this circumstance. If you look at it in the cross-section, then this is basically the mode profile that's E at the function of R and Z. Here we show it as a fundamental mode family, which is the mode we use. Specifically, it's transverse electric mode, which means that the electric field is along the radial direction. So basically, there are this mode profile. Usually, when they have the same mode file, we call it the same mode family. And there's an M number to decide which mode it is. And these two conditions give you a definite frequency of this mode. So everything is fixed. So for three fixed mode, we need them to be frequency matched to satisfy the energy conservation. This is usually easy in free space, but in microring, that's a major part of what we are doing. And the second thing we need to do is phase matching. In this case, if you are using single mode family, the advantage is that the phase matching is very straightforward. You want this M number to be conserved, and that's it. And you want to have a resonant enhancement, and that's a point to use microring. So we want high loaded Q for all three modes, and also we need the mode overlapping to be pretty good. So And then resonant waveguide coupling, basically the two things important, you need to inject the pump beam efficiently, couple the signal and light of the photons out efficiently. This, I believe John Saip and the other professor has mentioned it many times. So one thing, it's very important, is really single fundamental mode engineering. It's basically automatically solves some of the problem. The second thing, you probably don't know this phrase because I created it. So it's essentially mode splitting. I like to call it SMS, like short message service. But so this mode splitting thing is basically to use to identify the mode number. So we draw it here, and looks very easy. We have the mode number, but in reality, you actually cannot measure it. You measure the spectrum, you see the frequency, which mode it is. You don't really know. You can do simulation and try your luck, but sometimes it doesn't match very well. And for close band four-way mixing, which most people are doing in telecom band, even like 20, 30 modes, it's easy to count. You basically can say, I pump at here, and I count 20 modes, so these two are a pair. But in our case, they are separated like hundreds away. If you're going to measure them, you probably need tons of laser. That's very expensive and very time costly. So we need to identify these mode numbers. So this is, we have a paper a long time ago about this method, which at that time proposed it for different thing, but it's very useful. So what it does is that we do a coherent geometry modulation, and so after the modulation in the pattern, it only split one optical mode or one optical mode with certain M number. The other mode is unperturbed. And so modulation is very simple. You do a cosine or sine, and the modulation period has to be 2 times of your optical modes in order to build up the modulation coherently. So as a result, if it's not the same, then they will not be unperturbed. Here I basically draw instead of drawing 100 modes, I draw 4 or 5, so it's easier to see. Modulation is 8, like 2 times of 4, so if it's right, it gets splitted. If it's not wrong, it doesn't do anything. It's supposed to be like a ring, but now it looks more like a donut. So here is a zoom in of the micro ring. So the inside is the micro ring. You can see we modulate in the inside with the sinusoidal modulation. Here we basically have 2 times 162 modulation in a device. And as a result, you can see in the center mode here, we split into 2. It's single mode in telecom, so there's only one mode family. So they are everybody else are equally spaced, but in the center we are split into 2, actually up to 1 nanometer. So it's very easy to see. We can obviously do it for all other 3 bands, and that's what we do. So here basically it's 9 devices, and you can see we can change the modulation of the geometry. We can split different modes, and also in all 3 bands. So by this way, we can identify all the optical modes we are using. So here we pick 3 mode numbers that match the phase matching condition. The M number conserves. You can easily see it because it conveniently ends with 3. So we measure these modes with wave meter down to 0.1 picometer accuracy. The transmission is here. The Q for the pump is a million for loaded Q. The others we overcouple it. It's a couple of hundred for good reason for the extraction for the photon pairs, and these are all fundamental modes. Phase matching, we mentioned frequency matching. So the calculation shows us it's like 0.16 gigahertz. It's much smaller than cavity line width, so it works pretty well. We do a stimulated process before, so put pump and telecom laser in. We can see red light out. So both on the device and on the edge of the chip. So here basically is a lens optical fiber to cover the light out. We can also do spontaneous four mixing, which is a photon pair spectrum. We put a pump laser only. We can see that this mode indeed, the best frequency matched mode is the one that's brightest. We have some slight peak before at the side because they also match. So this one is particularly 444 and 162. The frequency mismatch is about 4 gigahertz. It's at the edge of each resonance, but it still have a little bit of efficiency. So we do some coincident measurement, which I'm not going to go to details, but this is a coincident CAR spectrum. So we use a peak CAR, basically the peak over the noise background. And at 46 microwatts power, we get about 5,000 pairs on chip pair flux. and the CR is above 2000. And if we look at, here we have 22 microwatts. I think the cartoon didn't show up. At 22 microwatts, we have pairs 1000 and CR of 3780. And at a high flux, we still have CR of 400. So this photon pair source is really wideband and narrow line width below gigahertz. CR is good enough for our application later on, and it's quite efficient and satisfies the requirements we mentioned before. To put our source in perspective with other visible telecom photon pair source, we plot the result in this figure. Okay, I just say it's among the best, and it's a nanophotonic device. So we do some time energy entanglement, and with different fiber lengths. We do it with 20 meter and get pretty good visibility of above 80%, and then we put 2 kilometer and eventually 20 kilometer in. The entanglement still keeps pretty well. So the other thing I will quickly mention is that we can tune this to basically whatever wavelengths you want. So if you need any wavelengths, let me know. I'm not going to go into the details. I don't have time. Future work, obviously, entanglement swapping, but also we are doing specifically for 606 for ion crystal quantum memory, and we are looking forward to do for silicon vacancy and other things. So we really need a collaboration there. Thank you.
Do we have any questions for Xiyuan? Yes, please.
Yeah, thank you. That was very impressive. Sorry, I have a technical question. So the modulation that you added to get the splitting for the selected modes.
Can you speak a little bit louder?
Oh yeah. So you added this modulation to the resonator to get this controlled splitting. Does that decrease your Q factor?
Well, it basically depends on how large modulation you need. So with this type of 1 nanometer modulation, it definitely decreases the Q by a factor about 3. But we have devices that have tens or even close to 100 picometer with still a million loaded Q. So it theoretically it should not, but in experiment it's a fabrication thing. You will be slightly lower, but you can keep it a million. So it's really useful.
Thank you.
Can we get the mic down here also?
So I was wondering, it looks like you only get generation in 2 modes. There's no, is that true? And how do you filter out if it's not true?
Well, in this case, I actually showed 2 sideband. So we have devices that doesn't have any sideband. In practice, you still put filter in just because you need to get the pump away. They have 40 dB isolation there, but you still put in. But yes, you don't need a narrowband filter for this purpose. Yeah.
All right, well, if we don't have any more questions, I'd like to close this session. Let's thank Xiyuan and all the other speakers in the session.
It's only the die-hard quantum people who are left. I have just a few comments because it's pretty late, and I want to thank everyone, all the attendees, all the speakers, the organizing committee, the volunteers who helped, Robin who organized so much, and of course our sponsors. So I was going to summarize the whole workshop in 10 minutes, then I decided not to do that. So I just pulled a few things that I learned. So Ryan was telling us that Feynman said that if you think you understand quantum mechanics, you don't understand quantum mechanics. So I took from that the first rule of quantum mechanics is you do not understand quantum mechanics. And the second rule of quantum mechanics is you do not understand quantum mechanics. If you haven't seen Fight Club, it's not as funny. The E field is bad. I learned that. I was scared straight. I'm never using the E field again. I told my kids, don't use the E field. There's a guy who's going to get you. It's the boogeyman if you use the E field. Is John Sipe here? Okay. Well, D and B field are good, though. That's what I told my kids. It's the Dave and Buster's theorem. So you can use the D and B field. So on a serious note, and just to wrap up, I want your comments about the workshop. And like I said before, I want to hear what you think worked, what didn't work, what we should include, if we should make it longer or shorter, or more invited speakers or more contributed talks, anything, because I think we're going to do it again. And you can send those comments to admin. That's the same email that was on the PFQ webpage. And I think you got the picture that we want to collaborate with you, that we're going to propose a quantum center. So we're looking for collaborators, visiting scientists, graduate students, undergrad REUs. I think we have 5 REUs at RIT. I think it's the most in the country. So if you have undergraduates who want research experiences with us, then let us know. We probably could figure out how to get them selected. We need postdocs, assistant professors, lateral move associate and full professors. So we'll be hiring a number of faculty very soon. If you are interested in that, let me know. If you know anyone who's interested, please pass that message along. So I made a little poem, a closing poem. In the year 2020, we will have photons aplenty. It doesn't quite rhyme. There'll be lots to do. Gonna have another PFQ. In the summer, though. Okay, that's it. Have a safe trip home. Oh, the government just opened, but I think it's too late for NASA, NSF, and NIST to make it, although NIST sort of made it. Don't tell anyone. Thanks.